Hi, I'm Subhaya Palani Ramalakshmanan as a part of EEE 236 class presentation on emerging technologies. This is What's Beyond FinFETs, primarily focusing on TFETs and BISFETs. Our first topic today would be on FinFETs. We would look at the basics of FinFETs, later move on to what's changed and what made FinFETs so popular. FinFETs, they get their name from their structure. FinFETs design use a conducting channel that rises above a level of insulator, creating a thin silicon structure shaped like a fin. This is called the gate electrode. The fin-shaped electrode allows multiple gates to operate on a single transistor. This type of multi-gate process extends Moore's law, allowing semiconductor manufacturers to create CPUs and memory modules that are smaller, faster, and consume less power. Some of the most recent products that uses FinFET's 14 nanometer technology are the new NVIDIA GTX graphics card, the 1080 that was released a couple of days ago. And this process was first introduced with Intel's Ivy Bridge E processors in 2012 with its 22 nanometer process. Gate wrapping around the fin allows much lesser leakage current to flow through. The graph here shows how the gate delay has been improved to a much smaller number by using FinFET process. The equations also provide the characteristics of saturated region, linear region, and the cutoff. The conducting channel being above the level of insulator also means there is more non-uniform current in compact models. And also, as the voltage increases, the current flows primarily along the edges of the channel. But FinFETs do suffer from an issue with capacitance, which we would see on later. So why are FinFETs so popular? Manufacturers were able to adopt this much more easily, mainly due to the fact that everything about metal 1 remains the same as the previous MOSFET processes. And also, economically, moving from 28 nanometer process to the 20 nanometer process using planar was unattractive, as it did not provide so much of a performance boost. FinFETs also implemented double patterning after 20 nanometer. So this needed a little bit of change to the place and route tool and also to the extraction tool. With FinFETs, the temperature change from the bottom of the transistor to the top was much different. This changed the threshold factors. And also, this did not have a need for any dopants. FinFETs do offer low operating voltages, which means better dynamic power and leakage power. Next up, let's see tunneling FETs or TFETs and the changes that they have over FinFETs. TFETs are based off of electrons' ability to penetrate barriers. This is known as quantum tunneling. Since chip makers stopped thinning the gate oxide, which really reduces what else could be reduced on a transistor, TFETs really changed the working of a conventional transistor. This is based off of electrons being able to tunnel through. Hence, by thinning the high K, we can induce more charge into the channel. But this does mean we need to have the on-off ratios pretty high. So the changes over FinFET are these have very low sensitivity. So with FinFETs, we did have 60 millivolt per decade, but now we would need to have something that's about 1 millivolt per decade. Since we need a large on-off so that to avoid any sort of leakage current. So to get a steeper turn on a higher current, it is not possible to do it through a tunnel barrier modulation. So we need to look into energy filtering. So we'd be also able to achieve higher current density, that is in order of 1 volt at 1 millisiemens per micron. Having a steep on off is one of the key areas where TFETs are better than FinFETs. Moving on to BISFETs and the changes. So BISFETs are based off of graphene. They are completely different from any transistors that we have seen before. They are two graphenes layers that are separated by a thin dielectric. They are largely in the labs in an experimental state, but let's just have a look on their working. BISFETs are non-charged devices. As opposed to TFETs and FinFETs, they work on interlayer rotation and free carrier and dielectric screening of electrons. And as the name suggests, BISFETs are bilayer pseudospin field effect transistors. The effects of BISFETs are not studied so much that it could be compared with a current day FinFET or a TFET, as they are more unstable and their characteristics are not set to a defined limits, and they vary per test. In conclusion, FinFETs are supposed to scale for the next two generations as per industry predictions, and TFETs are the most likely process to succeed them, as they have much in common with somewhat of a larger change than from bipolar transistors to field effect transistors. This would be a larger jump. And moving on to BISFETs, that would be the largest change the industry probably would ever see due to the material characteristics. Thank you so much.